related to Arduinos. So keep a few things in mind when dealing with Arduino. But then you have there's a kind of function. I don't remember how it's called, but I think it's analog, right? Which is shown in here, which kind of tells you that there will be some sort of additional development. You can identify that it is actually what Arduino technology is a PWM signal. Okay, so it assumes that you either take care of it or you don't care about the actual value. By taking care of it, I mean that you actually follow it with a low-pass filter, right? If you really want to obtain a DC or DC value of some sort. Or you are actually connecting that output to some sort of a driver, which will take care of it. Okay, so this is good to understand that there's no digital to analog converter within Atmel EE128 microcontrollers. We do have it in cases for that's a feature. In many cases, you still need to purchase an external if you want to use a DAC of some sort. Something I'll talk about later, but I prefer in many cases to use my own external DAC. Now, as far as analog output, digital output PWM. So pins 3, 9, 10, and 11 will output PWM signals at frequency of 190 Hz. Pins 5 and 6 at 980 Hz. Okay, so if you select the pins, you can output PWM signal. Right, so those are the frequencies. They are very low frequencies. It is not that Atmel cannot produce frequencies other than this. This is what Arduino library contains. Okay, that's something that Arduino is not a limitation of Atmel anymore. But you can program yours, but if you want to use it for some other frequency with some other frequency, then you have to reprogram it. Okay. Remember that the development idea is quite basic, but internally it is using a GCC compiler. Right? So which means you can program with Arduino IDE, you can also program conduct registered program. Okay, so you can program it as a regular microcontroller without using Arduino libraries. Those Arduino libraries are high level, high abstraction libraries, HAL libraries, how officially they're called. So which means an analog write or digital read or something, digital write or something, right? So it is very high level. You don't go into the registered programming actually to program it. So that's why it is so popular that even artists can use it. Actually, it was created for artists, pretty much. Those who are creative, who are doing things, Arduino was initially created not for us to use in many projects. Right, so keep that in mind. So you can still use Arduino board and Arduino development environment, what they call Arduino Studios, to program the AER microcontroller. They can conduct registered programming. Many students before used it just to program, or to do regular registered programming. So some students, I remember, were saying that, oh, I don't like, the students are using Arduinos. Oh, I didn't. You can still use it for whatever purpose. It's actually very useful. You can still do registered programming. If something is missing within Arduino library, you can create your own way. I didn't say that you cannot use it. Please use it. Except what I'm after is, do you know registered programming? That's my question. Not what you use. That's right. Okay. Keep that in mind. So that's the implementation of PWM. So since I don't discuss ADMO NDR, so that's the only thing that is available as far as RD. Right? And plus, I do assume that you have a sufficient background coming from 1 to 1B. And as much as I don't like it, the way they did it, yeah, that's what we have. So anyway, so with this basis, so since originally I planned to have, speaking of midterm, originally I planned to have a midterm on Friday, but Friday is off. Okay, so that's next week. So that's why we will have it on Wednesday next week. Okay, I don't want to delay to push it back to the 7th. All right, so midterm, so let me briefly review it. So on Wednesday next week, we will have our midterm. So it is open notes with every time. However, laptops, phones, iPads are not allowed. You can use a regular calculator. But you still need to have a phone or a laptop because you will have to upload your work to grade school. Okay, so it's in it'll be 10 minutes. Okay, so I will plan to test for 1 hour, 20 minutes. 1 hour, 10 minutes. All right, so 10 minutes will be to upload your work. Okay, so which means it stops the test at 10. All right, so you will have 10 minutes to scan your work and upload it to grade school. Okay, but otherwise, notes are not, I will not allow to use your iPad, tablet, phones, or course materials. Now, what type of questions are expected? Because I will post the practice midterm, so you will actually have a copy, the one that was offered before. So it will be in the same spirit. Okay, so I will not provide any questions, so those who know me, you know that they don't comment. Even if you find a typo in practice midterm, finals or tests, whatever, I just write it for reference, not for you to, you know, solve it or something. So question types. So true or false questions. Short questions. So they require short essays or something. Or description. I will show you examples. Long questions with multiple subparts. Okay, it is also possible. So for example, I write a piece of code and I ask for this or this. I'll show you. MCU programming related questions. So it is not that I'm asking it to remember how registers look like and which bits they contain. If that information is needed, I will provide it in the statement. Okay, so it is not that you have to remember names or mnemonics. However, you have to understand how to properly read information of specifications. All right, so this is one of my objectives, that you know how to read specifications, how to understand. So midterm is 15%, not much, right? But not much means the difference between B and A. Right, so 85 and 100, right? There's a difference. So please do not ignore that. Surprisingly, midterm scores like this, I don't know, it is not even a trend. It was always like this. Why? I don't understand why scores are lower than bigger. So make sure that you don't lose points. I mean, what's the point? Like the average was 75. I mean, fine, so but midterms were surprising always. Right? Permanent. Oh, yeah. Well, some of you probably already know why. That is not very happy because I do ask questions that actually I discussed during lectures and that do not appear in the slides. So this is to say that's an advantage for those who attend lectures. I do it intentionally. It is not that you cannot answer them, except that I'm discussing it. Right? So I provide more. Okay, so those are the topics that we covered on the midterm up to lecture 9. All material from lecture 1 up to lecture 9, right? So nothing is missing here. So all of it will be covered. So let me go briefly over some information. So, of course, I can ask questions that are indicated in any of my slides. So I extracted a few slides from my previous slides, just to show you, what kind of questions I may have. Okay, so a question, for example, how we develop a control application. So you have a couple of options how to do it. So what are the advantages and disadvantages of options, for example, to create a system using discrete components, right? So which is not quite flexible, right? Because if you modify logic or something, you will have to redo it. And for example, another option is to program it with MCUs. So it is easily reprogram logic. But what would be the disadvantage? For example, option 2 of using microcontrollers to program logic, right? There are multiple functions which you can do with logic, right? So what would be a disadvantage of using microcontrollers? So that's the type of question I may ask, right? So how would you answer? Show me like 2, for example, like 2 examples where we should use actually this. So what are 2 reasons not to use options? Any idea? We discussed it in lecture, right? So that's the type of question that you should answer in lectures. We did discuss it in lecture. All right. So what would be, like, give me 2 reasons why I would not use an MCU but resident discrete implementation. Guys, any ideas? Guys, let's discuss it. We can discuss it. We don't get any opinion about your work on the midterm. Well, before midterm, in between or something, I don't care. What I care about is what you get on the midterm. So I don't get any questions. So, Jeff, let's start with you. No ideas? Why would you not do why would
Maybe a cost, maybe?
cost? Okay, that's reason 1.
Time constraint.
Why? What would that constraint?
To make the project.
Well, I think with MCU you can make it very quick. Right. Okay, guys. No, that's why we use MCU, because we can make it fast, make things fast. Okay, so cost, right? Time probably, right? Expenses in terms of if you want to make a final product, right? Because it would require programmers, set up facilities instead of just placing automatically components with the machine. Right? So there are many advantages of discrete components. Well, disadvantages is in fact, and also speed of processing. Remember, MCU goes through the cycle, like analog to digital conversion or something like this. There are many things related to the speed of processing. There's nothing that can beat, like discrete implementation, because it is so tuned to the applications, so tailored to the application that the speed is incredible. Right? So anyway, so we have to understand the general computer architecture and the need for buses, the internals, and we need to understand the difference between MCU versus CPU. I discussed it many times, but that's what we have to do. So we need to understand the difference between 2 architectures, Von Neumann in the Harvard, which is also called Princeton architecture. So where program is located and where data are located. Okay, so data memory and program memory are separated in Harvard architecture, and they share the same memory space, or the same, now this is the same chip, this memory chip in Princeton or Von Neumann architecture. And again, so it is critical. That's a classical questions that they typically ask. Okay, so I do expect that I will ask again. All right. So in big endian notation for endians, the most significant bit is located at a lower address. No. Okay, so if your address is like 0, 1, 2, 3, 4, 5, most significant bit would be located at 0, followed by lowest significant bits in big endian implementation. In little endian implementation, the lower address corresponds to a lower significance bit. Okay, so that's what we have to understand. And you have to remember, yes, please.
So if it's big endian, the zeros would be on top, and A, B, C.
Exactly. So this would be 30. You would have 0, 0, 0, 0, A, B, C. What we have to remember, though, so it is not all. So what this is, remember, we also have to remember that in ARM microcontrollers are 32-bit machines. And the integer size in this architecture is 4 bytes, or 32 bits. Okay, so if I were to write only, but I can also declare an integer to be long, which is 64 bits. Okay, so in order to write a 64 bits, what machine the CPU will do, it will write first 4 bytes lower significance bytes, followed by upper significance 4 bytes. I understand what I'm after. Which means in big endian notation, it will first, so if you have, for example, I will write it in terms of hex. So let's say you have 0, 1, A, and then you have 0, 0, let's say 0, 1. So we have 4 bytes in here, followed by these. Okay, so let me separate. So we have 4 bytes in here, 4 bytes in here. How it will be written in memory. So this is long integer, right? Okay, so long. Because long integer is 4 bytes. Keep that in mind. So in integer and long integer is the same thing. Okay, so if you want to have it 64 bytes, 64-bit long integer, you have to declare it as long. Okay. You don't even have to specify integer because long corresponds to integers. But typically, don't omit. Don't rely on compilers. They're treating integers. All right. So how would that be given? So what would be written here? By this address. Like this. You see this lower address? 1000, 10101. So it is higher. So it is like ascending or ascending. So what will be written in here? What's that? CD. Exactly. Because remember, writing will be done by 4 bytes by 4 bytes. So 4 bytes at a time. Guys, is that clear? So if you have a big, that's why big endian notation, be very careful when you actually do it. Even though it is in many cases, no, it is critical even if you do CC. It is even more critical to understand it when you do C programming because you don't understand what's happening, you don't see it immediately. If you were to use assembly, you would see it. But there is some issue here. But the fact is, how it is written, you don't see it. And it may create a mess when you start writing into particular addresses information. So first, what it will do, it will write actually it will write 0, 1. Because first it will write this, followed by this. So it will be 0, 1 here. Okay? Most significant bit, it will open that. 880001, and then it will write that one. Everything is like reverse order. That's why I would never use that's why I never use big engine for anything. I learned so many lessons with that when I was using my first computer, which was Intel 8080 based, which I couldn't modify it. It had to use big engine notation, but the fact is it was the problem didn't appear that often because it was writing using quite small. Those problems appear very rare. So that's why I use little engine notation because these problems will never. Is that here?
So if we do little ending, it's like a short-term, right?
Yes. Yeah. So it will actually write again. Little engine. It will write the least significant byte first. So there will be no issues. It will actually write CD, AB, 0000, and then it will write that one also in that order. So there will be no issues whatsoever. You got it? So the little engine will never cause problems. Just long because it will first write this byte, which will be this. And then it will write this byte, which will be 01008801. So it will be very nice and clear. Okay. Is that make sense? Because think of it like this. Why this happening like this? Because it is writing byte by byte. Remember, CPU doesn't do anything. It writes one full bytes at the same time in one shot. So it is natural to expect what will be happening. Because all procedures are based on 4 bytes. Okay, so that's how CPU operates on numbers. And this is a type of true and false questions. So let's answer. Using a microcontroller is always a better approach to developing as a control system than using logic circuits. So what would be the answer? True or false? False. We discussed it. Right, so there are advantages and disadvantages. So keep that in mind. We always have a trade-off. We always deal with a trade-off. Now, microcontroller implementation guys are expensive. They're super expensive. Yes, they are more flexible, but they are more expensive. So that's the difference. Major difference. A64F uses the hardware, I would say modified hardware. Uses, guys, do not deviate even if there is a problem within the statement, accidentally, for example, right? Follow the statement. Okay, because it will be based on the statement. Remember, the class is about not just K64F, but in general microcontrollers. So even if it is not true, but it is stated in the question something, take that as though it is true. Okay? Is that clear what I said? So assume it is not K64, but K64M, DEF, whatever microcontroller. Okay, so we assume that it's just for fun. So K64F uses a Harvard architecture, so that's what we have to take into account. So Harvard architecture, not modified, not nothing else. Where data and program memory spaces are separated to reduce memory access latency. True or false? Sure. Now, 32-bit type variables can be declared and used in C language on 16-bit architectures like ATmega 328. True or false? True or false, guys?
True.
Like, think. So what does the size of an integer in ATmega microcontrollers? 2 bytes. So what would be long? Long? And by the way, long integer. No, it will be still long. Long would be 32 bit. Okay, because long integer was needed for 8-bit architectures, 1-byte architecture. So for 1-byte architectures that we were crossing only 8-bit numbers, which is 88, right? So it was, the C language was declaring that information as byte, referring to integers as bytes, right? So integer, 1 byte. Long integer was 16 bits, or 2 bytes. Long was 32 bits. So that's why we have these kind of conflicts with long, and so on and so forth. So that's one. So 32-bit type variables can be declared long. Okay, so this is the type of questions that I'm interested. So input-output port, guys. So we have to understand that how to actually how to generically how to enter information into these registers and how we can use it. So actually, which registers are needed to set up the general purpose input output. Okay, so remember that we have to provide a clock. We have to configure in for GPIO. We have to set up the direction and repeat or write data to work register. Okay, so this could be as if we want to output data, so that's the registers that we use. If we want to input data, we use input data, that's the registers. Those are different. The same thing is in ATmega. In 9S12 microcontroller that we used before in this class, actually it was a single register for both input and output. Okay, so that's when you switch over to another microcontroller, you have to check. Will you use the same register for both things? Or for input and output, you use different registers? ATmega, ARM microcontrollers, they use separate different registers. Bit operations, guys, so this is something that you have to have available because they may ask questions related to toggle a bit, a particular bit, or set a bit, or clear a bit. Okay? Or, for example, I may ask a question and give you a code to show me the problem with the code. Okay, so I'll give you a snippet of the code, right? And I was planning to clear the register, right? And then all of a sudden, I'm actually using this operation to toggle it. Okay, so we'll have to mark it as wrong. That's where the problem is. Okay, so there are different permutations how I may phrase a question, really. We do have to understand all these references. So we need to understand why this is critical, because in many cases you connect microcontroller to external circuits that may use different logic patterns. So we need to understand, can we actually use our microcontroller to connect to this type of logic pattern? Okay, so, or will we burn the microcontroller or the logic circuit? If we output something that the logic will not work, so which logic will not, that logic will not tolerate, then we'll get damage. So we have to understand what actually these things stand for. So VIH, that's what built about this value, so let me actually make the chart of this. So VIH and this is VDD. Okay, so VIH means the lower bound of voltage that the microcontroller will still interpret as high. Okay, so anything about this level will be interpreted by the microcontroller as logic 1 or true. That's what VIH is. VIL is actually the upper bound of voltage that the microcontroller will still interpret as 0. Okay, so anything here, any voltage in this range will be interpreted by the microcontroller as 0. Anything in here will be misread, which means undefined. Okay, so maybe you have to make sure that that's what's happening. Now, as far as output voltages, so that's what the manufacturer of this microcontroller guarantees as high or low. So, let me go again. So this is VDD, this is ground, right? So, let's say I include the break here. So V output I is the lower bound of voltage that the manufacturer guarantees will be as a low bound for 1, for true. Okay, so which means the manufacturer guarantees that if you say output logic 1, the actual voltage that will be present on the pin will fall somewhere in this one. So they guarantee it. Okay, so that's what the manufacturer guarantees. And similarly, output low, let's say somewhere over here, the output low. In this range, this will be the range that will be guaranteed by the manufacturer of K64M, for example, right? That when you say output logic 0, the voltage here will be somewhere in this range. Guys, so far so good? Now, when you match different logic levels, so our microcontrollers use 3.3 seamless logic family. Okay, so these days we have gazillions of logic families. 1.2 logic family, 0.8 volts logic family. So, and you may have a component, make sure that you check the component and its specification, what this component will interpret as 0 and high. 0 and 1. Okay, which voltages. So make sure that you read specification. Always, when you deal with components, guys, make sure that you have a documentation for all these components. Okay, if it's very rarely that they cast, I don't think I remember when I was doing it ever. I always have a specification, but formally, if you don't have a specification, you can actually do it by experimentation. What it interprets as 0 is 1, like any logic factor. But steep. Now, what? Okay, so is that clear? Okay, so for example, I may ask you a question. I'll give you a voltage. How it will be interpreted as a microphone? As simple as that.
Can you take a picture of that?
What's that?
Can you take a picture of it?
Sure, yes, okay. But they have it in my slides.
I always say I have a separate slide in the lecture.
So just extracted slides and information. So guys, I suggest that you review all slides and just read them once again. Okay, so just not work to I don't go beyond lecture slides. What I'm saying is that I may provide more discussion during lectures, but all the information that I require is in the lectures. Okay, so ask yourself questions. Another question is the type of questions that, for example, I may ask is, come up with your own problem. Okay. Ask yourself a question and answer. Assuming that you are designing a test or something, ask yourself a question and answer. Right? So this is the type of question I can answer. All right. So maximum current for each pin is 25 milliamps. That's what you have to remember. And overall, all pins together cannot supply or source or sink more than 100 milliamps of current. Otherwise, you will fry the micro. First, you will fry the pin and anything connected to it, all controllers. But maybe that you will damage the whole microcontroller. And assuming that we still cannot purchase microcontrollers with this AI craze and bitcoins, right? So they purchased everything. We still have issues with getting imports. So be very careful. We cannot purchase imports anymore if they are not available. Because manufacturers prefer to deal with those who order millions of parts instead of us who ordered hundreds of parts, like for the class. Right? Still, we're on a waiting list 1 hour, 1 year and a half. And go figure how to get it. And so you cannot sell it. So, right, so please make sure that these values are not exceeded. Because students do like to destroy them. Because they can't. Right? So that's a joke, of course. So make sure not to apply over voltage. If it goes above 3.6 volts, 3.6 volts, it is pretty much destroyed. You might not want to destroy. So it means you can connect Arduino to the microcontroller, right? Pins, and it will pretty much destroy. If you output from Arduino 1, because it will output 5 volts, you connect it to the pin and it gets destroyed. However, if you use Arduino to receive data from the microcontroller, it's okay. Let's say this cut in class, right? Because it was falling in that range, which will be probably interpreted by Arduino, and yeah, it will not damage anything because voltage will be lower than 5 volts, so Arduino will not be destroyed. And K64F doesn't care. Because it will produce out of the output voltage. Another way how to destroy an MCU. Okay, so these may be kind of questions. For example, describe ways how you can destroy an MCU. Okay? Give me two ways how to do it efficiently. Okay? And irreversible. Configure input-output pin to output, set it high, and connect it to ground. You're shorting the power supply. Okay, so all these things. So make sure that you don't. But I may ask questions, for example, on we have to remember how to do basic connections to the external world. So remember, you see, and I may ask a question. For example, a killer question. So I have an MCU with something, whatever, so it is like we have multiple pins or something. So to one of the pins, I'm connecting an LED. Can I do it? What's K64 then? Can you hear me? That's a good point. But can I do it with K64 then? Because we should support them with electric. They're kind of shaky. Exactly. There's an internal pull-up resistor which you have to do. Okay, so, another question if I may ask. So you do add a resistor here, 10K. And then you enable its internal resistance, which is also 10K. What voltage You understand the question, right? So internal pull-up resistor, if you enable it, right, this will be 10 degrees. Now you connect it like so on this pin, you enable the pull-up resistor, and you have such a connection. My question is, what would be the voltage in here? The pin will produce, which you will measure with the multimeter or something. So what would be voltage that you will make? Okay, so it will be, assuming your output in 1. So it will be what? 165? Half of 3.3 volts. Because it will appear in parallel. In parallel connection it is half. Okay, so your resistor will look for the circuit for the pin, for that controller that produces 3.3 volts as being two resistors in parallel. Two resistors in parallel will lower the voltage in the line. So equivalent resistance of two resistors in parallel is half of that resistance. Okay, so half. I did discuss pull-up resistors in lecture. I have witnesses. So, and similarly, interfacing with dip switches, right? So there are multiple ways how to do it. So you can either use, for example, these as pull-up resistors or pull-down. So different ways how to connect it and how to actually use it to connect the switches. So it will be, you will have sort of a positive logic or negative logic. Okay, so depending on how you connect it. So for example, if in this configuration, right? So if switch is in this location, so for example, let me answer such a question. So I will give you a schematic, right? For example, and I will say, okay, so this switch is right here in this position, right here. So it's well, disconnect pretty much. This circuit, right? So it is disconnect. So it is off. So this is broken circuit. What voltage will be here? So disconnected, connected. Okay, so the switch. So that's the slider is red. Assume that the slider is red, right? So if I put it here, this means it's disconnected. Okay, so what voltage will be present as the input of this microcontroller? If this is disconnected.
Maybe 3.3.
Well, whatever BCC. Right. All right. So now, on the other hand, if you put it here, right, in this position, so you close the circuit, right? So you are pretty much grounded at this point. So the pin will be, you will have to reach the zero. Okay, so I may ask questions related to this. I will provide a schematic. Let me show you what exactly you will have to detect, the 0 or 1. I provided different configurations in this lecture. So please review these configurations. So this is one with the setup. Another setup is when you actually disconnect it, it actually grounds. So please review those. Now, so there you see, like, this is just related to one lecture, actually, GPAO. So many things you can ask. So that's why you just don't, not just read the lecture slides, but actually try to ask yourself questions. So just to make sure that you understand what's happening. Now, interrupt program, or again, temperature warning, we have to run. This temperature warning is coming from this, or it is coming from here? That projector. I think there's a projector, but remember that I was switching over to PC and it was showing okay. There was no issue with PC, but all of a sudden there's an issue with the cloud. So anyway, so interrupt program. So we have to understand what these how to program interrupts and when we actually use them compared. So speaking of an interrupt itself. So interrupt, by definition, is a signal to the CPU, all right, which is generated by hardware or software. So it is clear that we can generate an interrupt by hardware. What kind of interrupts can come from software? Can you give me an example? That's a question. Give me an example that the software will generate an interrupt, what type of issue there would be, that can be.
Delay.
Like what?
Delay.
A delay, what would it be? Time delay, right? Time function. That would be a good answer. Yeah. But there are like some things that is not programmed, for example. Well, you'll have to capture exceptions, right? Those are for exceptions. Any other microcontroller. Yeah. ABR microcontrollers, exceptions, which are software interrupts, which are not interrupts, they're actually exceptions. And there are exceptions and interrupts, right? So ABR treats everything as interrupts. Exceptions refer to software, interrupts refer to hardware in all other microcontrollers. All right. However, for ABR, everything is an interrupt. Software or hardware, they're treated as a single word, interrupt. Okay. For example, what is blue screen? It is not that often anymore. In MS window, on MS Windows, I don't see it frequently. What happened to my laptop? Probably just once, I think, blue screen. But before that, it was infrequently met. Blue screen, boom, Bill Gates. Bill Gates here is here. Right? In case you forgot. Right? So that's what happens, you know. So for example, you read an instruction which doesn't exist and the CPU doesn't know how to interpret it. Okay, so that would be an exception. Right? So it reads instruction, but it cannot execute blue screen. But you can capture that. So when the my contemporary microcontrollers can actually capture that event, what this is. Okay? And it will trigger an event. If you don't process it, it will be blue screen. But the fact is that this can generate an interrupt which you can process. Alright? So that will be a software. So this is the type of question I make. You brought me an example of software interrupt. What was the requirement for software to process the software? So again, however, now if interrupt is captured, or you want to process some interrupt, that's the steps that you will have to do in order to program. So you will have to initialize the interrupt vector table. Right? You have to write the interrupt service routine and enable the interrupt. You should know where to look for these files for naming conventions. I may answer, I discussed that. So review. So where do you find that information as far as K64 address? Is it located in the main header file? Or it is located somewhere, someplace to enable conventions. So overhead of interrupts that we have to take into account, and that will be a disadvantage of using interrupts compared, for example, to round-robin request for processing. Okay? So, how many clock cycles it takes? Maybe hard to. And what actually is happening when we're saying saving and restoring of CPU registers? What exactly this means? Can you actually describe the process? What's actually happening during this stage? Saving CPU registers. So, for example, I will ask a question. So, during interrupt, I'm saying that information from CPU registers needs to be saved. Where is it to be saved? That's a question.
In cache.
What is that?
It would be kernel memory.
Which one?
Kernel?
What is kernel?
It's whatever is saved specifically for the system to use, not for the program.
Yes, and cache is a separate memory from RAM. Okay, so we store program and anything related to data in RAM. We don't have access to cache. Right? Cache is something that is implemented by hardware. Okay. So we don't have access to cache. It is a separate piece of memory within the within the chip. It is called L1 cache. The memory cache is called L1, which is located on the same chip as, for example, a CPU. There's L2 memory, or L2 cache, which uses memory which is outside, is located outside the chip. So there's a separate memory. You don't have access to it. Okay, so it is designed by architecture. It is processed by architecture. You don't have physical access to it. Broken access. Okay, so this story, can anyone answer that question? And I'm saying, saving CPU registers. Where is it saved?
In the ROM?
We're only read-only memory. Okay, so we're talking for so long about stack. I'm really surprised. That information is stored in stack. And it is read back, eventually, from stack. We have students here, guys, and I discussed it quite extensively, right?
What is it? I've read some specs, they have L3 cache, what's that?
That's a very different, that's yet another chip. Cache memory, like guys, if they use cache memory, if you repeat commands, because reading from memory, it takes time. External memory, right? So if you have an external memory hard drive, for example, right? So it is a very long process to read information and store information, right? But if some commands are repeatable, you repeat commands, and actually you can actually detect that and can store that locally to the chip itself. Okay, so L1 cache is very, very small, so it cannot store too many commands. So that's why they introduce L2 cache. L3 cache is more located somewhere in active control. But it's all related to the speed of processing. So we will not be discussing it because that's a class. I don't know if it was discussed in CS61, but if you are interested, take as a class CS161, which we are modifying right now to accommodate EE students. How many CE students are here? Okay, so we will have to take that. 161. So we are trying right now to rework the computer engineering program and to accommodate also EE students in these classes that are considered that may be useful in the future. So anyway, but it is something for the future. So anyway, so saving and restoring CPU registers is taking place in RAM, which is the upper address of RAM. Stack is assigned to the highest possible memory. So if there's a memory, let's say, containing like 256 bytes RAM, so the stack will start at address 255. And then it is going by loading the address. It goes up, but it's still under the RAM. Where program is located, where is the data are located. Like interrupt service routine is the highest memory, as the lowest memory address, 000. No, 000 is the interrupt. It's located where it's always where the program starts execution at address 4. Okay, yes. So and that's where the interrupt vector is located. Okay, stack is located as the highest possible address, and it is going by it is storing information by lowering its address. Okay, because it is the highest, and then 254, 253, 252, and so on and so forth. It's like stack goes up like that, and when you remove all the information from stack, it's very going down. But maybe if you store too much information on stack, it will interfere with program execution. Because they are located in the same RAM, in the same memory, in the same address space. So, polling and versus interrupt. So polling means that we are asking devices if they need attention, or they need an interrupt of some sort. Or they need, I'm saying not interrupt, but if they need attention to be processed. Okay, so it is done by the so-called round-robin process. So you ask device 1, device 2, device 3, and then go back to ask device 1, device 2, device 3, you know, like in this round-robin fashion. You're asking, do you need attention? No. You go to device number 2. Do you need attention? And so on and so forth. Interrupts don't need it, because once an interrupt is generated, the CPU will know which one actually wanted that attention. But the problem is that there are also advantages and disadvantages in these two processes. Polling requires permanent, process of asking devices for attention if they need attention. All right. Interrupts, on the other hand, they have overhead with CPU storing information from registers in the stack or not. Okay, so it is like always a trade-off. And another problem with interrupts is that you lose synchronization. So if you do real-time programming, most likely interrupts will be disallowed in your application because they are unpredictable. In round-robin polling, the cycle time is predictable. You can predict how much time it takes for you to ask devices for attention. Okay, so there are some companies, as I mentioned already in lectures, right? They actually disallow interrupts completely. Gone. That's it. No. Polling only. Okay. Because those companies actually do this real-time systems. So interrupts can be are efficient, can be ignored or masked, and they can be prioritized. So, for example, if you have two interrupts that appear at the same time, the CPU will decide which one has a higher priority to be processed. And interrupts can be nested. That's the problem, the biggest problem. Because interrupt, and with that interrupt happens another interrupt. When it happens another interrupt, the stack is growing, you never end up leaving. So this may happen. And debugging that is very difficult. Debugging interrupts is very difficult. I mean, compared to polling, just focus step in. If there's interrupts, you never know when it will happen. You have to actually properly, do debugging. I wanted to have a lecture on debugging. Maybe I will introduce it in the class, but I will definitely discuss it in scene design, hopefully. But it actually requires a separate lecture, actually debugging embedded systems. So interrupt service requests. So you set up all pins for inputs, outputs, set up the clock and stuff. What is critical is first you have to initialize the interrupt back and enable interrupts. Remember, once you are configuring interrupts, make sure that your system doesn't process any interrupts. So if you want to reconfigure some interrupt, disable all interrupts. Okay, because in the process you can actually decide, okay, it may be part of the program or the system implementation that you disable interrupts, then enable them, and then you want to reconfigure interrupts while it is still running. Okay, so in this case you have to, when you do reconfiguration of interrupts, make sure that you disable them for all interrupts, because it will create a mess. Okay, so if you want to modify, reconfigure interrupts during runtime, make sure that you stop or disable all interrupts. So in other words, NDIC, which stands for Nested Vector Interrupt Control, disable. It will be a command, disable all interrupts. In my slides I have that command, disable ISM under the underscores. Okay, so to enable interrupts on a particular port, remember that you enable interrupts, you cannot enable interrupts for a particular pin. Because all pins are attached to ports. You can, as far as GPIO type of interrupts, then you have to enable interrupt on a port. Then when interrupt happens on a port, within the interrupt service routine, you have to check on which pin this interrupt actually happened, unless there's a single interrupt on the port. So in this case, you know what, it's the same, you don't have to check because that's the only pin that was configured to receive interrupts, right? But if you have multiple pins connected to the same port, which would trigger an interrupt, in this case, within the interrupt service routine, you have to check, okay, so which one is actually was asking for information for interrupt, okay? So exactly. So anyway, so you configure the systems the way you were configuring for general purpose input output. This is for input output type of interrupts. Then you have to clear all the flags, because once an interrupt happens, there will be an associated pin flag that will be set. Once that flag is set within the register, it cannot receive interrupts anymore. So in order to receive new interrupts, that flag must be clear. So that's what this line actually does. Okay, so port A, apparently on pin 1, right, 0, 1, right? We have to clear the flag. Even, you see, I do it intentionally here, even though, since this is just the beginning of the code, it will, that bit will be cleared anyway. But I still do it, just to make sure. Okay, not to depend on it. What if some other routine or something configuration actually modified the bits by accident or whatever? I still disable it, or enable it by clearing that bit. And then I do go into while loop and sleep pretty much and wait for interrupts to happen. Now, once you get into the interrupt service routine, you will have to clear pending interrupts. Okay, not only just a flag, but clear the port A. Because remember that you enable interrupts on a port, not just on a single pin. So you have to clear interrupts on the port and then clear the interrupt flag on that particular pin. So there are two things that must happen. Okay, so examples are provided in the slides, and you already use them. So questions that I may ask are multiple ways. So for example, I may ask a question, why would you need, for example, why would you need this if you do this? Is that clear? So why do you need two things to happen? Why don't you just limit myself to this? You know the answer, right? Or just describe it. Because the first thing just tells the system to accept interrupts on that port. This tells us that make interrupts, allow interrupts on a particular pin of that port. There are two different things. So those are two comments. I know it is a good question, right? But so hopefully, you did labs on the interrupt, so you did, from what I hear, those labs went well. So the majority of students succeeded in getting interrupts. Now, analog to digital converter, there's multiple questions related to this. Okay, that I may ask. Okay, so input signal analog voltage, so we have to convert it into a corresponding digital. No, we have to convert an analog number into a digital number. Okay, right? So we have to establish the range. By default, it is from 0 to 3.3 volts, and it is set up on particular pins of a microcontroller. We don't do it in software. There are pins associated with analog to digital converter, right? And you can set them up for as a reference. Okay, so there will be, I don't know what else default, but there will be a pin, which will be called something like AD or something, or VADDD or something, so it is like related. So this will establish the upper level of the voltage that you will be converting. Okay? And there will be VSS, AD, okay, so later to represent one of these, which will establish the lower range of the voltage that it will be converting. Okay, so once the pins are, you select the pin for analog to digital conversion, right? You will have to establish the range. If you don't establish these voltages by physically connecting to particular voltages of interest, right? The default will be that the lower range is 0, upper range is 3.3. Or I still suggest that you actually do this. Now, precision is a number of distinguishable ADC inputs. So 12-bit converter, how was this number obtained? Yes. How was this number obtained?
2 to the power of 12.
2 raised to the power 12. Okay, so this will tell you how many actually levels. All right. So resolution is different. It is like what is the shortest range of voltages that you will resolve. So will it be, you can resolve 0, 1, 2, 3, 4, 5 volts, for example, or you will be able to resolve 0.1 volt, 0.2 volt, 0.3 volts, 0.4 volts. So this will tell you the precision of detection, right? So the range will be 1 volt. You have ranges levels 0, 1, 2, 4, 5, right? Or you will be able to resolve it with much more accuracy, right? So in this case, the resolution itself is simply take the range of voltages that you're detecting and divide it by the number of levels. So this will give us the resolution. Average conversion error, you simply divide this number by 2. And because you resolve, let's say your ranges are 0, your voltage levels will be 0, 1, 2, 3, 4, 5, right? So when it is 0.3 volts, so you will detect it as possibly 0 volts, right? So the error is 0.3, which is half of 1 volt range. So within 0.5 volts, you will be active on that. And that's why you divide by 2. So you should know how to apply properly the formula which is shown in the figure. Okay, so how to do the conversion. So this is the range of voltages. Let's say this is the value, actual analog value of the voltage. This is refers to this voltage, they're the same thing. Number of levels. All right. And given this will produce a digital number which corresponds to given analog voltage. Or vice versa, given analog digital value of the voltage, what analog voltage it actually corresponds to. So we have to know how to apply this formula into rearrangements. Guys, any questions related to this? Okay, remember that the range can change. So by default, again, we have 0 volts in here, 3.3 volts in here. But if you connect it, for example, between 1 volt and 2 volts, this range will change. Keep that in mind, and you can actually do it. So, for example, one way how to increase the resolution given given precision, right, 12 bits, and you want to increase the resolution of that voltage. But you know that your voltage will be between 1 volt and 2 volts, right? You can do it by simply changing the range of voltages that you will be resolving. So these 4096 levels will be between 1 volt and 2 volts, so the resolution will be increased compared to the resolution if your range is from 0 to 3.3 volts. You see, so like you have to always play with that. If you're guaranteed that you are interested only in this set of voltages, you want to have high resolution, you don't have to use a higher precision kind of analog to digital converter. Okay, so you have to change the range of voltage that you are resolving. We have to understand what the successive approximation method is, but that's what's used in the microcontroller for analog to digital conversion. Okay, so how it is set up. Okay, so please review that example. We have multiple examples in the slides. Don't want to waste more time on this, but the advantage, what is the advantage of successive approximation method compared to other methods? And give me again, why this type of an analog to digital converter is used in majority of microcontrollers as an analog to digital converter. Give me one reason.
It's the fastest.
The fastest would be the flash,
Yeah.
with resistors. That was, there's nothing that can beat it. But not the fastest, but there is some, why it is actually used in this way, we have to understand. The sync-developed approximation, like probability, different types of things. So what is actually why it is so frequently used in microcontrollers? Because its timing is predictable. So given the resolution, so for example, you want to obtain the value in the range of 1 byte, which means 255 levels, right? So the time that it will take to process analog to digital conversion depends on the number of bits that you are processing, because the process is taking place bit by bit. And that timing is predictable. So what is the successive approximation? We start from the most significant bit. We set it to 0 or 1, right? So we have an input. We have an input which doesn't change, all right? We have a controller which is doing all this successive approximation thing. So it actually produces a value of 1, 0, 0, 0, 0, like shown in this case. Okay, so that's what the controller will produce as a number. And it will start working on the most significant bit first. Okay? So once it thinks that this is 1, the most significant bit, this will go through a digital to analog conversion, and it will convert this value into a corresponding analog value. That's a digital to analog conversion. And then it will compare this analog value to this analog value, which comes from the actual input. If it is higher than that, right? So minus is here, plus is here. So if it is higher than this, it will say, oh, it is too big. The number is too big. So that most significant bit will be set to 0. Clear, right? Then it will move on to another bit. So now we have, for example, here 0. Now it will change the next bit to 1. So the most significant bit is now set, let's say, to 0. So it will try this number. So again, it will produce a corresponding analog value and compare it to the input. If it is still too big, it will say, no, even this is too big, so it will set it back to 0. And it will try another bit. And assume now that that value is lower, but it produces a lower analog value. So it will say, okay, now I have to keep it. Okay, so 1 will stay, and it will move on. So now these 3 bits are established. So it will move on, and we'll set this bit to 1. And again, we'll produce an analog value to compare it with a given value. Is that clear? So now if it says, okay, so it is still lower than the input value, well, it will set this bit. In this case, it will stop, because all bits are done, a figure. Okay, so it's the best it can do. Okay, so is that clear? And that's a process continued with all bits. So this is to say, the questions that I may ask based on this. K64F allows multiple precisions for analog to digital conversion. 8 bits, 12 bits, okay, no, 8 bits, 12 bits, 14 bits, and 16 bits resolution. You would like to have a very high resolution for voltages that will fall in the range from, let's say, 1 volt to 3.3 volts. So which analog to digital converter you will be using? The one which is 12, let's say, bits, or 14 bits or 16 bits. Let's say different between 12 bits and 16 bits, but you want to have the highest possible resolution. How will you do it? So which of these you will use? Discuss advantages, disadvantages. Of course, you can say, I will use 16-bit resolution, right? I mean, precision, in order to increase the resolution, right? But the problem is that 16-bit require more time for processing. What if your process is too fast and this 16-bit processing is too long? You actually may lose some information already. So what do? Change the range and lower the precision of the analog to digital converter, and your resolution will be extremely high at the cost of lower processing speed. Okay, so that clear? So there are many, when you set up analog to digital conversion, you actually have to think. Okay, because if you increase the precision, you increase the processing time. Is it suitable for your application or not? All right? So you have to ask yourself a question if it is suitable, because if your process is too fast, you will, while you are processing it, the input already changed. You understand? And you didn't react to it because you are designing a controller system which doesn't have a reasonable response time. Okay, so you at this time, okay, so now you have to reduce the precision by reducing the bit number of processing, right? So like say to 8 bits, right? But then I will have to reconfigure my range so that to process only voltages at high precision in that particular range of voltages, right? So there are multiple trade-offs when you actually design an analog to digital converter. Okay, guys? So signal conditioning circuit, guys. So this is to say, I may ask you actually to design, to rescale voltages, input voltages to a particular range. So either from 0 to whatever voltage to 0 to 0.3 volts, or whatever other range of voltage, or rescale with a voltage offset. So in this case, you will have to use this schematic. So please make sure to review these circuits to understand how examples are provided in the circuit, in the slides, but I also provided them to you. Okay, so please make sure to review. You have to have a general understanding of how registers look like. You have to understand C programming language, so I may ask a question related to actually the size of variables, different types of declarations, look for a mistake in the code. So for example, I can make it an intentional mistake in the code. Instead of this, for logic comparison, I may say, for example, instead of, for example, AND operation logic, I will say this. You will have to see that actually this is not a logic operation. So for example, in the if statement, right, I want to AND this and that. I produce 1 if they coincide, not 0, right? But on the other hand, I make a mistake and I indicate this instead of logic AND operation, right? So in this case, I will actually manipulate bits. I will not be doing anything logical. Okay, guys, so many questions related to programming. Okay, so like this one. So I guess this slide is uploaded to Canvas. So make sure that you actually review it. Yes. And questions related to the timing modules that I just discussed. So it is kind of this you have that fresh in memory. Okay, so I don't have to spend more time on this. Okay, and how to set up the timing module, how to set up input capture, how to set up output compare, so you understand what PWM is, what the edge aligned PWM is, center aligned PWM is. Okay, there are many questions that we cannot cover all possible questions in this short video. But are you getting the idea what type of questions I may ask? So kind of generic. So it is not asking for particular questions, except maybe for resolution and application, but it's also particular kind of my objective is that we have a general understanding what microcontroller programming is all about, K64 is about, and how we can read specifications. Okay, so guys, so we have to be flexible, to have a very good general knowledge of what's happening.